Moving on, we're going to be developing our logical power. But as we expand the power of our logical language, we have to take care. So we're going to develop the ability to make statements about objects. In other words, the statements that are either true or false are going to start carrying some meaning rather than just being letters. For example, we could take the statement, x is a prime number. Now, if x is a specific number such as 5, this statement is true. 5 is a prime number. True. If x was a different number like 6, the statement would be false. 6 is a prime number. False. But we could replace x with other things, for example, banana, and banana is a prime number is technically false, I guess, but honestly it's just meaningless. We don't want to apply this question of what is prime to things that it doesn't, really apply to. So we don't necessarily want to evaluate the statement banana is a prime number as either true or false. It's just meaningless. And even the original statement is meaningless. X is a letter or a symbol. It's not a number that we can talk about being prime. Now, when I first stated X is a prime number, we all intuitively understood that what I really meant was X represents a number and it hasn't yet been specified. And then this becomes a legitimate statement, but X as a symbol is not a number at all. So if we're going to make claims about things like this, for example, prime numbers, we have to have variables that we replace with certain things and not others. This variable x can be replaced with 5 or 6, and that's a reasonable thing to do, but I don't want to replace it with banana or mountaintop. That's just not reasonable. The collection of objects that are valid for substituting into statements is what's called the domain of discourse. The domain of discourse is the collection of objects that can be put into these special new type of statement. So let's talk about what sort of statements we're going to be developing. So statements that have variable inputs are called predicate statements. We tend to use capital letters to represent predicate statements with this parenthesis around the variable that is going to be replaced with elements of our domain of discourse. So if you just write something like this, it's not really a statement. Okay, for example, x is a prime number is not a statement until you replace x with an object from the domain of discourse. 5 is a prime number, that's a true statement. 6 is a prime number, that's a false statement. X is a prime number is not actually a statement until it is replaced with something from the domain of discourse. And remember, the domain of discourse is just everything that is what you're going to be putting into the statements that you get to pre-select. Okay, if you have a specific object in the domain of discourse, that's called a constant. So if I'm making statements about, whole numbers, then my domain of discourse could be whole numbers like 1, 2, 3, 4, etc. Any particular object, like the number 5 or the number 28, is called a constant. A letter that can be replaced with a constant is called a variable. Okay, this is stuff you've used before. We're just formalizing the language. Variables are, not actually things from the domain of discourse, and once you pick a specific element of that domain, a constant, and put it into the statement, it becomes a statement. So let's just suppose the domain of discourse is any real number, okay? We want to make statements about real numbers. So each specific number is a constant. So I could make a statement, call this statement capital P of x, and the statement is x is bigger than 0. Now for the letter x, it's neither true nor false because it's not a statement yet. But if I make a particular choice of constant, it becomes a statement. 3 is bigger than 0. That is true. By picking the constant 3, which is a real number, and replacing it into x, I got a true statement. If I pick the constant 0, 0 is a real number, and I could certainly pick it to substitute into this statement here. 0 bigger than 0 became a false statement, but it was at least a legitimate statement. But if I just left it as the letter x, this isn't even a statement because x isn't a number. It's not one of our constants. However, there is a way to make statements using variables so they are actually statements, and it has to do with using what are called quantifiers. Okay? They're going to give us a way to talk about these predicate statements, and the word predicate statement implies that even with the variable in there, it should be considered some sort of statement. So we can quantify predicate statements and turn them into actual things, actual statements that are either true or false. This backwards E is called the existential quantifier. And you interpret it as there is one, there exists some, or just there is. This upside down capital A is called the universal quantifier, and it stands for every, or for all, or for each. So we can quantify predicate statements using a quantifier that refers to the appropriate variable. So for example, if we have a statement p of x, then each of the following are now statements, even though they still contain the variable x. There exists an x such that p of x. That's how you would read this one out loud. We've got our existential, there exists an x so that p of x. So what this statement says is, in the domain of discourse, there is something so that p of x becomes true. This statement here, however, is what's called universally quantified. This says for every x, p of x is true. Okay, now these are both new statements that refer to when is the statement p of x true. P of x by itself wasn't a statement until you used a specific constant in place of the variable. But now what we're doing is we're saying, is there one choice of constant so that p of x is true? That's what this exists x such that p of x is claiming. And that's now a true-false statement, even without having picked a specific constant. There is a constant so that p of x is true, or for every constant, p of x is true. These are things that are now true or false, even though they don't refer to specific constants. A predicate statement might have multiple variables, and then every one of them has to be quantified in order to get a statement. So suppose p of x and y is a statement. You could quantify it in a bunch of different ways. So if you make a particular choice of constants, one constant for x and one constant for y, you'll get a legitimate, thing to talk about. For example, this could represent x is bigger than y. So sometimes this is true and sometimes it isn't, but once you pick two specific numbers, you can now evaluate this as true or false, in which case this would be read as there exists a choice of x and there exists a choice of y so that p of xy is true. And in this particular example of x being bigger than y, there exists an x and exists a y so that x is bigger than y. That's true. It is possible to pick two numbers so that the first one is bigger than the second one. This statement here is fundamentally the same thing, and we'll discuss that further. There exists a y and exists an x so that p of xy. Is there a choice of y and a choice of x so that x is bigger than y? Yes. But let's take a look at this statement. For any x, there is a y so that x is bigger than y. This is actually true. For any number x, there does exist a number so that x was bigger than it. That is a true statement. No matter what number you pick, there exists another one so that y is smaller. This statement, however, is false. There exists a y so that for any x, x is bigger than y. There is no choice of a number y so that for any number x, x is bigger than y. That's actually not true. Even though these look kind of similar, they're actually different. Okay, there's many other possibilities of how you could pick different quantifiers for predicate statements. So we're going to take a look at a few examples. So suppose our domain of discourse is real numbers. So any variable we have has to refer to a real number. We have a few predicate statements we can construct, like p of x represents x is bigger than 0. Q of x could be the statement x squared minus 6x plus 1 is less than 2. And R has two inputs, and it represents x plus y is less than or equal to 0. So the quantified statement, there exists an x so that p of x is true. Okay, p of x by itself is neither true nor false. It's just symbol bigger than 0 that doesn't have any meaning. This, however, is a quantified statement, and it's now true. This happens to be a true one. Does there exist a real number? Because remember, our domain of discourse is real numbers, so that's what variables refer to. Does there exist a real number so that this is a true statement? Yes. For example, 4 is bigger than 0. True. 98.1 bigger than 0. True. However, this is a false statement. For any real number, p of x is true. For any real number, x is bigger than 0 is true? No, that's actually not the case. It is possible to find numbers for which this becomes false. So it's not true that for any x, x is bigger than 0, and if it's not true, it must be false. And here we have a compound statement that we can quantify. There exists an x so that p of x and q of x are both true. It is possible to find a choice of x so that x is bigger than 0 and x squared minus 6x plus 1 is less than 2. For example, 1 is a number. 1 bigger than 0? Correct, that's true. 1 squared minus 6 times 1 plus 1 is less than 2? Yes, it is. So does there exist a real number so that p and q are both true? Yes, which means this is true. There exists an x so that both are true. How about this? For any x, there exists a y so that r of xy. For any x, there exists a y so that x plus y is less than 0, less than or equal to 0. That's actually true. Notice we're not making a specific choice of x and y. The statement we're evaluating is for any x, there is a y so that this is true. Yes, it is the case that for any number x, there will exist a number y so that x plus y is less than or equal to 0. Okay, but what we're doing is we're claiming something about for any x. So for any choice of a number x, can I pick, does there exist a y so that x plus y is less than or equal to 0? That's what this statement says. And yes, if I pick y to be the specific number, for example, negative x minus 1, x plus y becomes just negative 1, the x's cancel, and then this becomes a true statement. So for any choice of x, is there a way to pick y so that this becomes true? Yes. Notice, however, that negative x minus 1 is not a constant. I'm not making one particular choice of y. What I'm saying is, for any x, it is possible to pick y. I'm not picking y and saying this is the one y that will work all the time. For any x, there is a y, and that actually changes. Okay? So if x has been chosen to become a constant, then this negative x minus 1 becomes a different constant. Okay, continuing, we have the same domain of discourse, real numbers, and the same three statements. We're just going to keep talking about these. So we've seen that for any x, there exists a y, so that x plus y is less than or equal to 0 was true. No matter which number x you pick, there is a way to pick a specific y to make this statement true. But if I switch these two things, now it's false. What does this say? There exists a number y, so that for any number x, x plus y is less than or equal to 0. That's not true. I cannot possibly find a particular choice of y so that for every choice of x, this is true. Okay, there's no number y that makes this true for every choice of x. So if you have multiple quantifiers, the order really matters. The statement, the predicate statement r of xy didn't change between these two things. And this was for every x, and this says for every x. And up here, there exists a y, and here there exists a y. But all we did was change the order of those two things, and it vastly changed what the statement was. It went from true to false just by changing the order of these two things. So if you have multiple quantifiers floating around, the order might critically change what the statement is. Quantifiers don't even need to always show up on the left. For example, this is totally fine. There exists an x, so that if p of x is true, then for every choice of y, q of y or p of xy. Okay, so this is still a legitimate statement as long as every variable has been quantified to the left of it. Okay, so where do the y's occur? They occur here, and those have been already quantified. The x's occur here, and they're quantified off to the left. Okay, that's really what needs to happen. Before any variable appears, it has to have been quantified, but it doesn't necessarily mean that every variable has to be declared right away. And in fact, if you took this universal quantifier here and stuck it outside, it would change the statement. So where they appear is really quite important. Okay. And specifically using r, p, q, r, and so forth, this just says there exists a number x so that if x is positive, then for any real number y, either one of these two things is true. Not necessarily both, but at least one. That's actually true. Why is this statement true? Well, remember that a conditional statement is vacuously true if the hypothesis is false. So is there an x for which p of x is false? Yes. which makes this conditional statement always true no matter what happens on this side. So since there exists an x for which that number is not bigger than 0, there does exist an x which makes this conditional statement always true, even when y is allowed to be whatever number it wants, and it's kind of for a silly reason through vacuous truth. All right, but hopefully we've gotten the impression that predicate statements can be a bit more confusing, or much more confusing even, than the single letter statements we've worked with up until now. But the good news is they're much more powerful. Quantified statements allow us to make statements about other objects, possibly even other statements, and claim some sort of truth that says something about those objects. In the first unit, little letters just represented true or false, but we were very clear to say we're not claiming any sort of meaning, we're just sort of getting used to the rules. Now we're going to start talking about statements that really do refer to things and carry information about those objects. And that's much more powerful, but it can be more confusing. So P of x might be a statement that sometimes is true or sometimes is false, depending on which constant you choose to plug into that predicate statement. However, the quantified version, like for any x P of x, that's a statement about whether or not a specific predicate statement is always true or not. So it's a statement about a statement. For any x is the statement P of x true. So since we're allowing statements to be formed referring to other statements, we can do a whole lot more here. And the rules of how we prove things are going to have to be expanded to accommodate this new flexibility. So we're going to be a little less formal in this discussion than a previous chapter. It will make discussion a bit easier to absorb.